So let's continue talking about RNNs, recurrent neural networks. So we're going to spend some time on them today, and then we'll probably talk about them a little bit more next class as well. Okay. So we have so we have our initial hidden states. We have hidden states corresponding to each word, and we have formulas for computing hidden states from previous hidden states in the current word. So and we also have word vectors corresponding to each word. So let's just remember the formula for this. So we have h1 is equal to what? It's equal to wh times, let's not forget, so we see there's a general formula here. The next hidden state is computed as a sum or some combination of the previous hidden state and the current input. So you're combining previous hidden states, current inputs at each time step to get the next hidden state. And I mean, there's various different formulas that people use here. This is just about the simplest thing that you can do. Similar, but not quite the same as something called the Ellman network, which was basically the first recurrent neural network was from UCSD. Jeff Ellman, who was in this department. People came up with much better RNNs. We'll talk about some reasons why this particular one doesn't work so well, but like they all share in common this general property. Like, what's the general property they share in common? So common across all RNNs. So all RNNs. What's common is that let's say hi plus 1. So the I plus 1 hidden state is some function of the previous hidden state hi and the current word, or the word wi plus 1. So this is the common property across all RNNs. We're instantiating this in a particular way here. It's very, very simple. And so further developments in RNNs, they basically involved what exactly should this function look like, this function f. Any questions about this? Okay. We need to get an output from this network. And we'll talk about some different things that we can do to get that output. Let's talk about one particularly simple thing that we can do with this, which is what if we want to do sentiment classification. If we want to do, or any binary classification problem, or any multi-class classification problem. That's fine. So what we need to do is we need to be able to, for any classification, any sequence level classification problem, that means we have our text. We want to assign a single class to that text, happy or sad, or is it spam or not spam. Any classification problem that we want to do, we need to be able to look at the entire text. There's only one hidden state in this sequence that has information about all the text. What hidden state is that? It's the last one. The last hidden state is a function of all the previous words. If you were to change any of the previous words, in general, the last hidden state will change. That's not true for h2. h2 doesn't get to see happy. Okay, so we're going to use the last hidden state for the purposes of classification. So we'll have our output value O1, so an output score. Maybe let's actually call it a vector O. So O is equal to WO, so W output, times H3. So this is going to be basically a vector of scores for however many classes that we have. And then we'll have a probability distribution P, which is equal to softmax of that. So we're going to turn our scores that are in O into a set of probabilities in P. And then we're going to have a loss function, which is our normal loss function. So loss is going to be equal to negative log probability of the correct class given our vector P, whatever that correct class is. We're obviously going to learn these W's, the capital W's here. We basically have three weight matrices that we need to learn. We have the output weight matrix, the hidden weight matrix, the input weight matrix, WI. We need to learn those things. The way that we're going to learn them is through something called, it's through backpropagation. We have a loss. We need to calculate how does the loss change when we change each of those weight matrices. It's a little bit nastier than the previous backpropagation examples that we've seen, but it's nothing, there's nothing actually new there, but it's a little bit nastier to work through. I think we're going to work through it next time. I decided not to do it today, but it's just an application of everything that we've seen so far, just repeated application of the chain rule. It does have some very weird properties, though, that we have not seen yet. as a lead up to understanding those weird properties, I'd like to actually look at something. It's related, but it's not quite that. Let's look at a very, very long sequence and what happens. So imagine, so we have we're building a spam classifier. Let's see. So if it's 1,000 words, that's 1, 2, 3. Okay, so what's this weird setup that I've drawn here? So I want to build a spam classifier. I want to take in a sequence like this, determine is it spam. The way I'm going to do that is look at the entire sequence, run it through my RNN. I get out a final hidden state, H1006. Why is it 1006? Because we had 6 words, and then 1,000 other words I'm not showing you. But assume that they're all the words from the Llama Llama Red Pajama books. Now, this is spam. We have like a link here, let's say, embedded in the beginning text that gives us the site where we'll buy our illicit pills. Then we have children's books after that. We should classify this as spam. What's the problem? We're going to be running H1006. Well, we're going to do H1006. We're going to send it. We're going to have we're going to multiply it by this matrix WO. That's when we turn it into scores for the 2 classes. Spam, not spam. We're going to get a score for each of those. We're going to softmax them or sigmoid, whatever. We get back probabilities for spam, not spam. And then that's going to be the probability that we get. So what's the problem with why might this not work? Yeah. Exactly. So let's think a little bit about why we're going to lose that information. So all of the information about this thing being spam is contained in the hidden state H3. That's going to be the only place where the model actually sort of sees that this thing was spam. That's where all the information about this was recorded. Now we get to H4. H4 is a function of H3 in the word llama. So the model at this point doesn't know whether the spamminess information it doesn't know whether it's going to be seeing more spammy information in the future. Or maybe llama is part of the spamming, right? Maybe who knows what they want you to buy for the llama. It's going to be H4 will now include information about both H3 and about the word llama. H5 will contain information about this word llama as well as the information from H4. So at each time point, we're mixing the old information about spam with new information about the incoming words. If you do this for long enough, the information about all those words in the beginning will start to disappear. It will just be overwhelmed by the new information that you're adding on. So RNNs in general have a very, very difficult time using contextual information from the distant past. It just gets lost. Whereas this is the concern you always have to worry about with an RNN. It's loss of information about earlier in the sequence. Any questions? Okay. This is related, but it's not identical to another problem which we'll learn about next time, which is called the exploding and vanishing gradient problem. This is another problem that comes about from the fact that you are sending information through very, very, very long sequences of function applications. So you're applying the same function over and over and over again. There's this RNN function. It applies to H4, then H5, then H6, then H7. So you're sending information into the future from very far back in time. This is another problem that results from that. So we'll talk about that. So it's a problem for doing backpropagation in RNNs. Okay. I want to now talk about another major application of RNNs besides classification and how we would go about doing it. And that is called language modeling. And language modeling is what language models, as you know them, primarily do. So we're going to introduce language modeling today, and then basically we're going to be studying it for the rest of the quarter. So language modeling does not mean anything having to do with language. It refers to next word prediction. Another more precise way of saying this is learning a probability distribution over sequences of words. So we're going to be trying to learn a probability distribution P that assigns high probability to frequent words and low probability, to frequent sequences of words, and low probability to infrequent sequences of words. Okay. So any probability distribution, so again, W1 through Wn are words, any probability distribution over a sequence of words can be decomposed. And this is just it's any probability distribution over any sequence can be decomposed in this way. And this is something called the chain rule of probability, different from chain rule of calculus. So how is it decomposed? You first say, what's the probability of choosing the first word? So you get that. You multiply that by what was the probability of choosing the second word given the first word. You multiply that by what was the probability of choosing the third word given words 1 and 2. And you keep going in this way until you get to the last word, where the last word is generated given the full context, w1 through n minus 1. So what we're saying here is we've just used just sort of a mathematical law. Okay, this is not something that we're inventing here. It's not something that we're doing specifically for language modeling. This is just a law of probability distributions. Okay, we're using this law in order to transform this very hard problem, which says if you give me a sequence of words, give me back the probability of that sequence. That's ridiculously hard. Like these are going to be this sequence these days may have 100,000 words in it. So I want to be able to give the machine a sequence of 100,000 words and ask it what was the probability of this sequence of words. I'm turning that problem into a sequence of much simpler problems. So instead of asking what's the probability of the full sequence, I ask, imagine the sequence was being generated incrementally. What would be the probability of this sequence being achieved? So I first ask about the probability of generating the first word, then generating the second word given the first word, and so on. So where is next word prediction coming in here? Well, it's in each of the terms here is a next word prediction problem. This is generate the next word after the first word. This is generate the third word that comes after the first two words. So I have n different next word prediction problems that I'm solving. Any questions about this? No, okay. What does this have to do with RNNs? Well, we can solve, or we can train a network to do language modeling with an RNN in a very straightforward way. How would we do it? So let's say that I want to train a network, an RNN, to do language modeling. What I mean by that is I want to train a network such that if I give it a partial sequence, it will tell me what's the probability of the next word after that sequence. And we'll do that for any sequence. If I have such a network, I can use it to generate sentences or generate text. So how would I build such a network? Yes?
Same thing we're currently doing, except instead of taking sentiment and predict, we're going to go over.
Okay, so just take the very last one there. Is that the very last word? So Thomas is happy. Predict the next word after happy. That would be the idea. Okay, let's try that. So what we'll do is we'll map this to, I'll put in a little circle here. We'll call it an O vector. I'm going to call it O3. The reason I'm calling it O3 is because it's the output vector that corresponds to the third hidden state. And we'll map this to another vector, which is P3. And so P3 will be a distribution over the entire vocabulary. So we're going to be asking our model to predict the next word that comes after happy. Maybe it's like the word and, or maybe it's a period. It's not necessarily a word, it's just a token. So we'll ask the model to predict what comes after happy, let's say. Good, so this is a classification problem, right? We have a correct answer. There's only finitely many classes that the correct answer can fall into. Classification. It's a, question over here? Yeah. Yeah. I mean, so the idea would be like we literally show it this text. So we're going to be pulling down text from the internet. We're going to be pulling down billions of sentences from the internet, showing these sentences. And so we show part of a sentence and we ask it to predict the next word after that part of the sentence. Does that answer the question? So I just described the training protocol. I mean, I didn't describe backpropagation yet here, but it's just backpropagation. I just compute a gradient. But there should be something. So you may be confused about the right thing here because there's something that's not quite right about this. So we're not done here. We're not done. But no. But if anyone is confused right now, that's good. So I'd like to answer any questions about that. No. Okay. So there's going to be some word that comes after this. The correct word will be like there's an actual sentence that we pulled down. Let's say the actual sentence that we pulled down from the internet is let's say the next word is today. So at the point of H3, the model has not seen the word today. We're going to ask it to predict today is the next word that's there. And this is a naturally occurring sentence. Okay. The way that we've set this problem up, we've shown it an entire sequence, or a large fraction of a sequence, and we're asking it to predict the next word that comes after that. What's the problem with doing things this way? Does anyone see a potential issue with this? Yeah. Well, that's true, and that's a persistent feature of all language modeling. That's correct. So this P3 vector here, O3 and P3 are each going to be the same dimension as your vocabulary. So those are big vectors, like 50,000. And that means that your output matrix here, WO, that maps from a hidden state to the output predictions, that's going to be a very big matrix. This is a persistent problem in all of language modeling. That's it. No, it's a problem, but it's not a problem that we can solve. Yeah. Okay, that's a great question. Where do we stop? So the answer to that is we choose a maximum text length. That's basically going to be our maximum context length. Maybe it's 1024. That would be a common one. With RNNs, it's actually much tinier. It's like 128 or something. That would be, you're not going to get, you're not going to get too much better performance by if you're using a plain RNN like this. Long texts are very, very hard to deal with. So your you're going to choose a maximum context length, and you're going to take your corpus, your set of data, and you're going to break it up into contexts of length 128, and feed those contexts into the R, and then predict the next word at, choose some word in that within that context, predict the next word after that. So you definitely have to do it. I wouldn't say that's the central problem here. Yeah. So that's a persistent, I don't know what to call it, it's exactly a problem, it's a persistent feature of language modeling, which is you're asking the model in some sense to perform an impossible task. How are you can't read someone's mind, how are you supposed to predict what the next word is? So the best thing that you can hope to do is have the model take into account as much context as possible to narrow down what the likely next word is. So maybe you're never going to be able to perfectly predict what the next word is, but what you can say is it's probably one of these 4 words. That's still, if you've narrowed it down to 4 words, you've learned a lot relative to where you were starting with. But yeah, what you're describing is like what I would call like irreducible uncertainty or irreducible noise, essentially, in the language modeling process. It's there, but like that, like so. Don't think of language modeling as a problem that can be perfectly solved. Think of it as a problem that can be, solved up to a few bits, basically. Yeah.
Is it that after today, the next word, predict the next word after today, you have to take that into account what today's problem is not the correct next word?
Well, so today is the correct next word by assumption. We've fed.
I guess like if it predicts the next word isn't today, but then it has to generate a word after that, it wouldn't take today into the context, I guess.
Okay, so you're getting a very important point, which I'm going to get back to in a few minutes. But yes, so let me get back to that question. Okay, yes. Well, so that's very closely related to the question over here. And so what I would say is that any particular sample does force the model to make one discrete choice. And you're right, there are multiple words that are okay there, maybe probably from the perspective of what we want the model to learn, like any of those words is okay. We're telling the model, if you do not get that particular word correct, like you're punished, right? So maybe you might think that's not good, but the hope is that we're showing the model, billions of different sentences. And so over those billions of sentences, it will see a lot of examples sort of similar to this where different words occur. And as a result, it will learn, oh, there's actually multiple possible words that occur after Thomas is happy. But many, many words are not okay there. You're right, though. On any given sample, we are penalizing the model if it doesn't get exactly this word right. Okay, let me describe the problem I have in mind. You're all raising some valid concerns about this, but let me tell you the issue that I have with this, which is what we've done here is tremendously wasteful. We have an entire sentence. Let's say this is a full sentence here, last words today. We have a full sentence here worth of data, but we're only making a prediction about a single word. That's a problem. We should be predicting every single next word in this sentence. That's going to be making the most use of all the data that we have. So at h0, we should be predicting what the first word of the sentence is. That might seem like an impossible task, but like we want the model to produce plausible first words of sentences in general. And it's not like first words of sentences are completely random. Some words are more likely than others. We should make the model predict what the first word is. So how are we going to do that? We're going to feed h0 through a linear model, make it predict o0, a probability, and then we get probability distribution over first words in the sentence, p0. So this is the distribution over first words. What about this? At Thomas, we should be predicting the next word, which is. So we get a vector O1, a vector P1 of probability distributions over the second word in the sentence. So what word comes after Thomas? We want to learn that it's. So the point is, in language modeling, if someone gives me a text, there's a lot of supervision signal in that sentence or in that text. Look at it over here. To produce a text of length n, I've broken down the problem into n different problems, into n different subproblems. Produce the first word, produce the second word given the first word, all the way up to produce the last word given all the previous words. Each of those n different subproblems can get supervision from a particular text. So I want to squeeze as much information out of this text as I can. What's my loss going to be? My loss is going to equal probability of Thomas given, it's going to equal negative log probability of Thomas is happy today. What's that equal to? That's equal to negative log probability of Thomas times probability is given Thomas times probability happy given Thomas is times probability today given Thomas is happy. It's negative log of 4 things being multiplied together. What's my rule? Is that I can take that as a sum of log probabilities. So I sum together the loss on each of these 4 different prediction problems. So that's equal to a sum from I equals 1 to 4 of the negative log probability of word I given words, let's say word 0 up to word I minus 1, where I'm assuming word 0 is basically saying like you're at the start of the sentence. You have to do funky things. Basically, I'll just, a word of caution here, I'm not going to emphasize this today, but like, you have to do slightly funky things. It's nothing too funky, just slightly funky things for the first word in the sentence, because like, what's the context before that? You need to know the sentence starts here. So usually you'll have a special token that basically tells you, hey, you're at the start of the sequence. That's what we mean by word 0. It's like a starter sequence token. So we have, for this one sentence, we have it has 4 words. Each of those 4 words gives us a new prediction problem that we're training our model to solve. If we only predict one word at a time, that's extremely inefficient. We're wasting all this information from the sentence. Any questions? How are your final projects going? Yeah, thumbs up. Have people been using GPT-4 productively? I mean, in this case, is it actually helping? Yeah, that's good. Getting some nods, very enthusiastic nods, so that's very encouraging. I'm happy to hear that. If you are avoiding eye contact with me right now, I would recommend starting your project sooner rather than later. So I'll be getting you feedback on the project proposals like by tomorrow. But from what I've seen so far, things are looking pretty good. So you should just like get started, I think. Yeah, I'm very excited to see what everyone's able to produce. Okay, I'm gonna talk about one more thing. So we talked about how to do language modeling with an RNN. This is for training the RNN. What would we do? Okay, let's actually talk about two more things. What would we do for sampling from a language model? So after training, so how do we generate from a language model that has already been trained? How do we do it? So if someone gives me an RNN, what is an RNN? An RNN is just three-weight matrices. No, it's not for us. An RNN is just three-weight matrices. WH, WI, WO, and I guess an initial hidden state as well, H0. If someone gives us those things, that's the full definition of the RNN. So someone trained these things. They did backpropagation through this loss function on a big text corpus. They trained the model to do next word prediction really, really well, or as well as you can do it with an RNN. What do I do with this thing now that I have it, if I want to generate text? Yeah. Okay, so I have basically the start token, or like H0. Let's say that H0 sort of represents the start token. We'll be more careful about this later on. But for right now, let's just say H0 represents, like, this is the start of the sequence. It's the representation. Okay, so someone gives me this. What do I do now? So it says you're the start of your sequence. So I compute O0 from this. So I compute O0. So this is like it's a little weird. I get out a probability distribution, P0. This is the probability distribution over the first word. What do I do with this distribution? Yeah. So there's not going to be any dot product. These are actually probabilities here, right? So this is a list. It's a list of probabilities. One probability per vocabulary, per word in your vocabulary. So there's a probability for the word the, a probability for the word a probability for Bob. There's one probability for every word. That's one thing you can do. Now, let's say we did that. So it's a common decoding technique. But I'm starting to generate a sentence from the very, very start. So what will happen if let's say I release a language model that does this type of, it's called like greedy decoding. If I do greedy decoding after I release my language model, what will happen as a result of that? Yeah, it'll be the same sentence every time. So we want a little bit of variety, at least in this setting. We'll talk about where we actually do want to use greedy decoding in a second. Okay, so what do I do if I don't want the same sentence every time? What do I do? Yeah.
So you have some constants ranging from like between 0 and 1.
Yeah.
And let's say the constant is 0.1. So you're like the 10% of most likely words you choose for those.
So that's interesting. So what you just described is something that was actually only discovered in 2020 or 2021, I think, which is called nucleus sampling. So there's a little bit of a twist on that. There's something even simpler that you're proposing a slightly fancy way of doing this. There's a simpler thing that we can do. So we have a probability distribution, one probability per word. What can we always do with a probability distribution? Sample it. So I'm just going to sample from it. So choose a random W1 first word given your probability distribution P0 over the vocabulary. So I choose my new W1. I insert it over, let's say it's over here. So I have W1. Maybe it's like Bob. I chose Bob. Okay, now I compute the hidden state corresponding to Bob, H1. And what I do now, I just repeat the process. So I have O1, P1. What's P1? P1 is a probability distribution over the word that comes after Bob. So what comes after Bob? I don't know, maybe it's like is or was. So I sample from this. The point is I'm going to sample from it. Okay. And I'm just going to repeat the process until I get to the end of the sequence. How do I know when I get to the end of the sequence? Usually I'm going to have a special end of sequence token that says here's where you stop. And I just hard-coded that as soon as I get to an end of sequence token, that's when I stop generating. The alternative is that I just keep generating until I get to a maximum context length. That's another possibility. Yeah. Oh, so you mean, well, let's not talk about the starting token because I'm being a little bit loose with how I'm describing this right now. Let's say how you get H0. Can you take a guess how you can get H0? What does H0 have to do with the loss? Exactly. We can just learn H0 like we would learn any other parameter in the network. If you don't know it, use backpropagation to learn it. That's a pretty good, pretty good way of thinking about it. So what input is that? So what I was considering right now was just how you get a language model to just generate random text from its distribution. So the language model learned a distribution over text sequences. How would you get samples from that distribution? And the way that you do it is just one word at a time. You have it sample the first word, then sample the second word, then sample the third word. Eventually, you're going to get a sample from this probability distribution. So that was the first question I was asking. I think you're asking the question is like, what if you ask the language model, what if you give it a prompt? You say, I want you to do this for me. How would you get it to sample from that? Is that the question? Okay, great question. So that's what I was talking about here was called unconditional generation. So this is just like generate random text for me, where the random means according to that probability distribution that we've learned. This is not honestly such an interesting thing because like maybe like it's gonna like produce like fake Twitter threads for you or something, right? Like it was trained a bunch of Twitter data, so it's just gonna generate like a random dumb Twitter thread that didn't even happen before. Like you don't want that. That's trash, right? So unconditional generation is not such an interesting like thing to do. But if you can do unconditional generation, you can almost always do the much more interesting conditional generation. So conditional generation means someone gives you a prompt, and you want the text completion given that prompt. And the way that we do conditional generation is almost the same as unconditional generation. So how do we do, if someone gives us a trained RNN, how do we do conditional generation? So they give us a prompt. Someone choose a prompt, a very, very short prompt for me, so I don't have to write much. Yeah. Today is. Okay. So here's my prompt. Today is. How do I use this prompt to generate conditioned on this prompt? So what I want to know, what is conditional generation? Conditional generation means what's the sequence of words, W3 through WK, that come after today is. That's the distribution I want to sample from. So what are the likely word sequences that come after this particular prompt? How do I use my pre-trained RNN to sample from the sequence? Yeah.
So would you just do the same thing as in week 5 and start with like 8-0 and then 8-1 and then out A?
Okay. Exactly. So it's going to be exactly what we did for unconditional generation, except that we don't care about the probabilities that came out of H0 and H1 because we already know what the first and second word in the sentence are. So we ignore the probabilities that come after H0 and H1. We only start with the probabilities that H2 produces. So H2 produces O2, which then produces P2. This is the probability distribution for the third word in the sentence. And maybe we sample from this distribution P2 the word A. And we keep going in this way. So we sample the word A, then that produces the hidden state H3. That produces a new sequence of probabilities over what's the next word after today is A. We sample from that. Okay, it's in the conditional generation setting where this issue of how to do decoding becomes much more interesting. So the decoding algorithm, decoding basically means is another way of saying generation given a model that's already been trained. It's just the term for it. So the decoding algorithm is basically like how do you select the next word given a trained language model. So for the purposes of this, there are fancier things that people do. Honestly, I'm pretty skeptical of almost everything fancy that's been proposed because they die out. It's like it's a very, very sad thing. People propose lots of fancy stuff. None of it really robustly works with the next generation of models. So there's two things that are the standard practice that we'll focus on. So the first one is sampling. Sampling is just what we've been talking about. So sample from the distribution, your probability distribution. It says the word A gets probability 2%. So 2% of the time you select the word A. You select words according to their probabilities. The other standard thing that people do is what was already proposed, which was greedy decoding. Greedy decoding means the following. After we see the word is, there is some word that's the most likely word. There's some word that gets the highest probability. Always select that word. That's all that greedy decoding says. Greedy decoding is interesting when you're doing conditional generation. So if someone gives you a prompt and you want to know what happens after that prompt, that's when people use greedy decoding. Sometimes. Why is that? Let's say someone gives you a math problem. So the prompt is a math problem, and you want to know what's the most likely, what's a good continuation after the math problem. You don't necessarily want a random sample from that distribution. Like you want the right answer. You don't care about everything the language model thinks is possible there. You want to know what's the thing the language model thinks is the most likely. So you're going to select the best word at every step. Now here's a puzzle. We're selecting the best word at every step. That's what greedy decoding says. Is that necessarily the sequence that has the highest probability? No. Good. Okay. I was a leading question, but you were very confident about that. So why not? Exactly, you can get stuck. That's exactly right. So the first few words, those each have very high probability, but then all the words after that, like it's very, very diffuse, the probability. So everything's just sort of spread evenly over all words, and as a result, the best word has very, very low probability. Whereas it could be the case that you can take a hit early on in probability in return for later on getting a much more likely word. This is a subtle point, honestly not very relevant for the day-to-day practice of language modeling, so we don't need to worry about it. There's a solution that people used to use, which is called beam search. I used to teach what beam search was, but it doesn't work very well in practice, so I don't teach it. These are basically the two things that people do. Sampling of some sort. There's a little bit of interesting stuff that we'll still discuss here, but it's basically sampling. So you have your probability distribution, choose approximately in proportion to what the probability distribution says, or greedy decoding, choose the best next word, highest probability word. That's what people do. Let's end there. I'll see everyone next week.